Well, the hyperbola may not be the most common shape around, and we might not see it too often in architecture. But when it is used in architecture, holy cow, is it obvious. Right? Here in Seattle, our most obvious example, as I had on the previous PowerPoint, was the Space Needle. Right? The legs of the Space Needle are hyperbola. Both the outer shape of them and also the little inner like cutout shapes. So let's go back and look at the previous PowerPoint if you want to relive that, or do a Google search of Space Needle images. But if you can look at some of the architecture that's been flying by here, sometimes it almost looks like the architect is the one to make an interesting statement. But in the case of some of the lighthouses and water towers, I'm sure it's a good way of being structurally sound with using a minimal amount of materials. So, previous lesson we had the hyperbola centered at the origin. Of course, now what happens if we take the hyperbola and move it away from the origin? I will have the materials on this slide available as a download. I'll probably have it saved as both a Word document and as a PDF, so whichever format is easier for you to download. And again, just like the ellipse, the x is squared, the y is squared, and it's equal to 1. But unlike the ellipse, notice it's subtraction in the middle, not addition. And then when we're looking for the value of c to find the focus, notice that we do a squared plus b squared instead of a squared minus c squared. Okay, so let's walk through a example step by step here. And again, if you hear some chickens clucking off in the distance, they're leaving those footsteps in the sand. So we can go through step by step and make sure that we get what we need to have. So step number 1 is in the correct order. Yeah, I've got my x squared followed by my x. I've got my y squared followed by my y. And then I got my plain old number set equal to 0, so that's looking pretty good. A1, do we have the leading coefficients of the squared terms 1? And no, we don't. I see a 9 on the x squared, and as tempting as it would be to divide everything by 9, that won't solve the problem with the 16 on the y squared. Alright, so I'm going to have to factor the 9 away from the x squared, and I actually need to factor a negative 16 in the y squared, right? Not just 16, but a negative 16. Now, of course, 9 times x squared is 9x squared, but what is going to make the negative 126x? Well, I need 9 times 14 for 126. So I'll have a negative 14x there. How do I get a positive 64y? Well, negative 16 times negative 4 makes a positive 64. Right, as usual, I gotta be very careful with my positive and negative signs. Step number 3, eliminate c. So I'll subtract 233 from each side of the equation. My personal favorite step of the bunch. So I've got 2 different b's I have to consider. I've got a negative 14x, so I got to take that negative 14. I'll have to divide it by 2. Then I have to square that quantity. So a positive 49 will have to be placed after that negative 14x. Hey, I've got a negative 4y. So I got to take that negative 4, divide it by 2, square that. And so I'll need a positive 4 after the negative 4y. Now, of course, when I place these values in the parentheses, I have to think about the total value I've added to that side. So when I place that positive 49 in with the x squared minus 14x, I've really added 49 times 9. That's a value of 441. So I have to add 441 to the right-hand side of the equation. Looks like I need to add 4 in with the y's. So I have y squared minus 4y plus 4. But when I put a positive 4 there, I actually just added a value of negative 64. Negative 16 times 4 is negative 64. So if I added a value of negative 64 to the left-hand side of the equation, I must add a value of negative 64 to the right-hand side of the equation. And now we will factor. Of course, I tidied up the right-hand side of the equation. And now I'm thinking, well, for the 49, I'm thinking negative 7 times negative 7. And then, of course, for the other one, I'm thinking negative 2 times negative 2. Right, because I have to multiply to get the constant term, but then they need to add up to be the coefficient. So we've completed the square, but the ellipse is supposed to be set equal to 1. Divide everything by 144. And of course, because 9 times 16 is 144, the fractions reduce quite nicely. Right? 9 over 144 is the same as 1 over 16. 16 over 144 is the same as 1 over 9. Now we are written correctly in standard form. Now I prefer, instead of referring to that sheet of paper that had all these mysterious, bizarre formula on it, I prefer to actually just think, hey, how am I going to graph this? Well, I better figure out where the center of this whole system is located. And so if I see x minus 7, I've got to think positive 7. If I see y minus 2, I got to think positive 2. And so the center of the whole system will be at 7, 2, and I even put a little dot on my graph paper there. Now, because the x squared is positive, the vertices are going to move in the x direction, left and right. Underneath the x squared, well, there is a 16, which is just 4 squared. So I have to move 4 units each way. And sometimes I actually find it easier to put the dots on the paper first, move 4 units to the left, move 4 units to the right, and then I say, hey, the vertices are 3, 2, and 11, 2. Right? I'm building off of that center at 7, 2. Right? Added 4 to the x-coordinate to get the 11. Subtracted 4 from the x-coordinate to get the 3. Now, for the foci, I've got to figure out the value of c. So this time we add, right? Again, I'm not adding 4 plus 3. I'm doing the 4 squared plus 3 squared. So I'm actually adding the 16 and the 9. 16 plus 9 is 25. Square root of 25 is 5. So from the center, I have to move 5 units to place the foci. So if I'm at 7, I can go 5 units right and 5 units left. So the foci are going to be at 2, 2 and 12, 2. Now with the asymptote, remember from last time, we've got to place the asymptote, excuse me, with the hyperbola, we have to remember from last time, we have to place the asymptotes. There, I maybe got that sentence in the correct order finally. And so I need to draw that rectangle that helps me define the asymptotes. So underneath the y minus 2 squared, I see a 3 squared. So from the center, I have to go up and down 3 units. All right? So I've got a rectangle now. The rectangle goes through the vertices. And then I went up and down 3 units. And it's the diagonals of that rectangle that are going to be my asymptotes. So now that I've drawn them, if I actually want the equation of them, I could look at my graph and say, oh, one of them is going up with a slope of 3/4. The intercept is at -3. The other asymptote has a slope of -3/4. Its y-intercept is +7. And again, there's some weird equation that we could use to decipher that. I prefer to actually graph it and just look at the picture. Whatever method works for you is the method you should use. And so now I can actually graph my hyperbola. Right? They will approach the asymptotes, and they have to go through the vertex. And just like a parabola, you know how the parabola wrapped around the focus, the hyperbola will wrap around the focus also, right? It's almost like there's 2 different parabolas on the same picture, although the shape is quite different. The parabola is actually much more U-shaped, while the hyperbola, well, it does have the rounded part by the vertex. It's much more of a V shape because as it goes off toward infinity, it approaches those straight lines, those asymptotes. So hopefully we'll have some smooth sailing. Oh, look at that worksheet go up and down like the waves. And there is one of those lighthouses where the design of the structure is actually a hyperbola.